So let's take a look. So review problem 3A. We have just one linear equation that's homogeneous. So we can say let W be the set of all vectors x1 up to xn in Rn such that a1 x1 plus a2 x2 and so forth plus an xn is 0. So you can notice first that the 0 vector is certainly in W, because a1 times 0 plus a2 times 0, if you let all the x's be equal to 0, you get 0. So W contains the 0 vector. And if you take two vectors, x1 up to xn and y1 up to yn are in W, then the x's are a solution of the set of equations. So a1 x1 plus a2 x2 up to an xn is 0. And a1 y1 plus a2 y2 up to an yn is 0. So, because each of these is a solution. But if you add these equations, a1 times x1 plus y1 plus a2 x2 plus y2 up to an xn plus yn is 0 plus 0, which is 0. So this is another solution. So the sum of these two vectors, which is x1 plus y1 down to xn plus yn, this is in W because this is a solution. So the set W of all solutions is closed under vector addition. And for all scalars C, if I multiply this equation by C, 0 is the same as C times 0. So that's C times a1 x1 up to an xn. I can distribute and rearrange, and this is a1 cx1 up to an cxn. That's 0. So that says that the vector cx1 down to xn is in W. So the set W is closed under scalar multiplication. It's closed under vector addition. It contains 0. Therefore, it's a subspace. That is, the set W of vectors in Rn satisfies the three necessary conditions for a set to be a subspace. Okay. So that's the proof of 3A. And 3B is the similar problem, but not for one equation, but when you have a system of equations. So this is 3B. You have a system, a1 x1 up to a1 and xn equals 0. am1, you have m equations in n variables, and W is again the set of all vectors in Rn. I'll just say are solutions. So it's all vectors that are solutions simultaneously of all these equations. But again, I'm not going to write it all down now, but again, if you let all the x's be equal to 0, you get a solution of each equation. So the 0 vector is in W. And if you have two solutions, you just add corresponding pairs of equations, and you see that W is closed under vector addition. And you also check is closed under scalar multiplication. So the three conditions for a subspace are satisfied. Right? So there's more, I mean, on the exam, you should actually write down everything I was just saying in words. I wrote it down for the first example, A, and the arguments are exactly the same for B. And problem 4 is to prove that if you have simply one inhomogeneous equation, that it's an affine subspace, so long as there's at least one solution. So you can't have all the, you could have the equation 0x1 plus 0x2 plus 0xn equals 1, and that has no solutions. So I should have added, we also have the condition that at least one of these coefficients, ai, is different from 0 for at least one I. In that case, there's always a solution of this equation. And so suppose we let W be the subspace of solutions of the homogeneous equation. A1x1 up to A1 an xn equals 0. So I proved a moment ago in problem 3 that this is a subspace. Suppose we let, I don't know, C1 up to Cn and be a solution of the inhomogeneous equation. That is, if you put in C's here, you get B. And so if you take another vector, C1 up prime up to Cn prime, you could say, so, and let L be the set of all vectors, I'll call them C1 up to Cn in Rn, that are solutions of the inhomogeneous equation. Okay. So if C1 prime up to Cn prime is any other vector in L, then what we have is A1 C1 up to An Cn is equal to B, because this is a solution of the inhomogeneous equation. And A1 C1 prime up to An Cn prime is equal to B, because this is a solution. And what happens if you subtract? If you subtract, you get A1 C1 prime minus C1, An Cn prime minus Cn equals B minus B, or 0. So that says that this vector C1 prime minus C1 down to Cn prime minus Cn is in W. And C1 prime to Cn prime is exactly this vector plus C1 down to Cn. Right, this is just C1 plus C1 prime minus C1 at C1 prime. So every vector that's a solution is equal to a fixed vector plus something in W. So this is in C1 to Cn plus W. This is an affine subspace. So if you take any solution, you take fix one solution to the inhomogeneous equation, take any other solution, and that other solution can always be written as your fixed solution plus something in W. So it's in a translate of W, and the translate of a subspace is what we call an affine subspace. And conversely, if you take this plus something in W, and you write down the linear equation, you get B plus 0 equals B, you get a solution. So again, there's more to write down than I've written down, but everything that I said constitutes a proof that's required. It's always the case that there are many different ways to prove a result. This is one way, and you could always come up with a different way.
Professor?
Yeah.
So Jessica wants you to solve question 8 through 14 and then 17 and 18. I would also like to ask that as well.
So question 8.
She typed it in chat, 8 through 14 and then 17 and 18.
Oh, okay. Happy to oblige. So problem 8 is to show that the inverse of an invertible. So what's the definition? So A is an n by n matrix. So an n by n matrix is invertible if there exists an n by n matrix B such that A times B, this is defined because the number of columns of A equals the number of rows of B, and B times A equals the identity.
I'm sorry, Professor, could you center the paper? Thank you.
Yeah, this is just a definition of an invertible matrix. A matrix is invertible if there's another matrix B such that A times B is the identity and B times A is the identity. So but then B times A and A times B is the identity means exactly that B is invertible and A is an inverse. So we proved that the inverse of a matrix A is unique. What that means is if B and C are matrices such that AB equals BA is the identity, and also AC and CA are the identity, then we can say that B is always B times the identity. And the identity can be written as A times C, so that's B times AC. And because matrix multiplication is associative, this is BA times C. And BA is the identity, is C. So if B and C are two inverses of A, in fact, they're the same matrix. So the matrix is unique. And because it's unique, we'll just denote it by A to the power minus 1. So this doesn't mean 1 over A. It doesn't make any sense. This means the inverse of the matrix A. So if A inverse, and A inverse A is the identity, that means on the one hand, A inverse is the inverse of A. But if you look at A inverse, it says that the inverse of A inverse is A, because A times A inverse and A inverse times A is A. So If you read this equation correctly, you've proven this. And suppose I take AB and I multiply it by B inverse A. So by associativity, this is the same as A times B inverse A. I haven't changed the order, I've just changed the steps by which I'm multiplying this. But BB inverse is the identity. And the identity times anything doesn't change the anything. So this is AA inverse equals the identity. And if you multiply in the opposite direction, so this should be inverse. B inverse A inverse times AB is B inverse A inverse AB is B inverse identity B is B inverse B is the identity. So the inverse of AB is B inverse A inverse. That's what we had to prove. Okay. Any questions?
Wait. Yeah. So I was with you when you had A, when you were showing that A times the A inverse is the identity. But what I just was lost when you said that the inverse of the A inverse was A. I don't understand that.
Well,
So yeah.
So we say that B is the inverse of a matrix A if AB is the identity and BA is the identity, right? That's the definition of the inverse. Okay?
Yeah.
And the inverse is unique, so we let A inverse denote the inverse of A, okay?
Okay.
And we can say C is the inverse of A inverse if C A inverse is the identity and A inverse C is the identity. This is the definition of the inverse of A inverse, right?
Okay.
Well, but we have that A inverse is the identity and A inverse A is the identity. So let C equal A. It works. So C is the inverse. So the inverse of A inverse is A.
Okay. That makes sense.
Now, to compute the inverse of a 3x3 matrix, one way to do it is you write the matrix 7, 0, 2, 0, 5, 1, 2, 2, 1. And we want to do a series of elementary row operations that put this in reduced row echelon form. And if it's going to be 1, 1, 1 in reduced row echelon form, we've somehow calculated the inverse. So what I do is I write the identity matrix. So instead of 3x3, I adjoin another 3x3 matrix, which is this identity. And then step by step, I put this matrix in reduced row echelon form. So I could, for example, I want a 1 here, so I could divide the first row by 7. So I'm not changing the second row or the third row at this time. I'm just dividing this row by 7. I get 1, 0, 2 over 7, 1 over 7, 0, 0. And then I want a 0 here. So I have the first row, the second row, and I multiply the first row by 2 and subtract it from the third row. 2 minus 2 is 0. 2 minus 0 is 2. 1, I'm multiplying this row by 2 and subtracting. 1 minus 4/7 is 3/7. 0 minus 2/7 is minus 2/7. 0 minus 0 is 0, and 1 minus 0 is 1. Then I want to get a 1 here. So I don't do anything to the first row or to the third row at this point. Sorry. So 0, 2, 3/7, minus 2/7, 0, 1. And I multiply this row by a fifth. And then I want to get a 0 here. So I have my first row. This should be a 7, I think. And this is my second row. And I take the third row minus twice the second row. So 0 minus 0 is 0. 2 minus 2 is 0. 3/7 minus 2/5. So 3/7 minus 2/5, I put that over a common denominator of 35. That's 15 minus 14.
I think it was 1/5.
Well, but I'm multiplying this row by 2 and subtracting. So it's 3/7 minus 2/5, which is exactly 1 over 35.
Yeah.
And this is minus 2/7 and minus 2/5. And 1 minus 0 is 1, I believe. So it's minus 2 times this plus this. Yep, okay. And then I want this to be a 1. So I multiply this row by 35. I get 0, 0, 1. When I multiply this by 35, I get minus 10, minus 14, 35, 0, 1, a fifth, 0, a fifth, 0, 1, 0, 2/7, 1/7, 0, 0. So if I've done this correctly, 0, 0, 1, minus 10, minus 14, 35. I want a 0 here, so I multiply this row by minus a fifth and add. I get 0, 1, 0. Minus a fifth times minus 10 is 2. Minus a fifth times minus 14 is 14 over 5. Plus 1 over 5 is 15 over 5, or 3. Minus a fifth times 35 is minus 7th. And then we get this top row at the same time. I want to multiply the bottom row by minus 2/7 and add. So I get 1 plus 0, 0 plus 0, 2/7 minus 2/7. See, minus 2/7 times this is minus 2, is 20 over 7, plus a 7th is 3. Minus 2/7 times minus 14 is 4. Minus 2/7 times this is minus 10. So if I did the arithmetic correctly, this is the inverse of the matrix I started with. And I never do this without making a mistake. So let me just check. I started with the matrix 0, 7, 0, 2, 0, 5, 1, 2, 2, 1. And I might have the matrix as the inverse, 3, 4 minus 10. Let's see, 2, 3 minus 7, minus 10, minus 14, 35. So when I multiply, I get 21 minus 20 is 1. 28 minus 28 is 0. Minus 70 plus 70 is 0. That's lucky. See, this row I have 10 minus 10, 15 minus 14, minus 35 plus 35. And for the last row, I have 6 and 4 is 10 minus 10. 8 and 6 is 14 minus 14. Minus 10, minus 20 minus 14, minus 34, plus 35 is 1. So that's kind of a miracle, but it seems like this is correct. So that's the process. Right. See. What was the next question you wanted me to do? Let me look at the chat. 8, 9, 11, 12, and 13. Okay. So let me look at number 11. So suppose V1 and V2 are linearly independent, and I want to consider the vectors V1 plus 2V2 and 3V1 minus V2. So I say, suppose we have scalars that say x and y, such that x times the first vector and y times the second vector is 0. I must show x and y are 0. But I can rearrange this. This is, see, xv1 plus 2xv2 plus 3yv1 minus yv2. Let's see, I have v1. I have x plus 3y times v1, and I have 2x minus y times v2 equals 0. But v1 and v2 are linearly independent, so x plus 3y has to be 0, and 2x minus y has to be equal to 0. And for this system of equations, the only solution is x equal y equals 0. So v1 and v2 are linearly independent. Then v1 plus 2v2 and 3v1 minus v2, they're also linearly independent. So that's half the problem. If this set is linearly independent, this implies that v1 plus 2v2, 3v1 minus v2 is also linearly independent. And now we want to try and prove this in the opposite direction. So suppose v1 plus 2v2 and 3v1 minus v2, this set of vectors is linearly independent. Suppose xv1 plus yv2 equals 0. We want to show, in this case, x equal y equals 0. So this is a little bit more complicated. Let's see, what can we say? I want to express v1 and v2 in terms of these vectors. So, for example, I have v1 plus 2v2 plus 2 times 3v1 minus v2. The two v2s cancel. This is 7v1. So v1 is 1/7 v1 plus 2v2 plus 2/7 3v1 minus v2. And similarly, so this is expressing V1 as a linear combination of these two vectors. I want to express V2 as a linear combination. Well, actually, that's easier. If I add these two equations, V1 plus 2V2 plus 3V1 minus V2, that's equal to sorry, that's not what I want to say. I want to say it differently. If I take minus 3 times V1 plus 2V2 plus 3V1 minus V2, the V1s cancel, and I get minus 7V2. If I've done this correctly, minus 3V1 plus 3V1 is 0, minus 7V2. So V2 is equal to minus the seventh times this, or what is 3/7 V1 plus 2V2 minus 1/7 3V1 minus V2. So this enables me to write V1 and V2 as linear combinations of these two linearly independent vectors. So I plug that into this equation, and I'll end up with two equations in two variables whose only solution will be x and y equals 0. And that will do it. I mean, it's a certain amount of work, but sometimes you have to do some work. Any questions about any of this?
When you multiply, you say minus 3 times B1 plus 2B2 plus 3B1 minus B2. Like, what do you do with the minus 3? Like, you just multiply, you just subtract the 3 from the other?
I don't understand. Are you asking about the second equation, this line at the bottom?
Yeah, that line at the bottom.
Well, so what I want to do, you see, what did I do in the first half of the problem, which was the easier half? I knew V1 and V2 were linearly independent, and I wanted to prove these two vectors were linearly independent. Now I want to prove, and the way I did that was, if x times the first of these vectors and y times the second is 0, that gives me an equation like this. And since V1 and V2 are linearly independent, I know that x plus 3y has to be 0 and 2x minus y has to be 0. That is, I get these two equations and two unknowns, and I solve these equations. I didn't solve it on this piece of paper, but I can tell you, and you can check, if you solve the equations, the only solution is x and y both equal to 0. So I wanted to repeat that argument in the second half. In the second half, I'm told that these two vectors are linearly independent, and I want to prove that V1 and V2 are linearly independent. So I say, if there's a linear combination of V1 and V2, xv1 plus yv2, which is 0, I want to show that implies that x and y are 0. If I do that, I'm done. So I want to replace V1 and V2 by expressions in terms of these vectors that I know are independent. And so, for example, if I take this vector plus 2 times this vector, I get 7v1. So v1 divided by 7, v1 is equal to this. And if I take, so what I did from this is somehow eliminate the v2. I next want to somehow eliminate the v1. Well, if I multiply this by minus 3 and add to this, I have minus 3v1 plus 3v1. That's 0. The v1 goes away. And I'm left with minus 7v2 minus 7v2. So if I solve for v2, I just divide by minus 7. I get 3/7 minus a 7th. I get this. So let me just say what the next step would be. So 0 is xv1 plus yv2. but V1 is 1/7 V1 plus 2V2 plus 2/7 3V1 minus V2 plus YV2, but I can write V2 as 3/7 V1 plus 2V2 minus 1/7 3V1 minus V2. So if I just rearrange, what is multiplying this vector V1 plus 2V2? I have 1/7 X plus 3/7 Y times the vector V1 plus 2V2 plus 2/7 X minus 1/7 Y times the vector 3V1 minus V2. And that's supposed to give me 0. But I know these vectors are linearly independent. So we have the coefficients have to be 0. 1/7 X plus 3/7 Y is 0. And 2/7 X minus 1/7 Y is 0. Or if I want to get multiplied by 7, I have X plus 3Y is 0. 2X minus Y equals 0. The only solution of this system of homogeneous linear equations is X equal Y equals 0. So I'm done.
Oh, okay. Thank you, Professor, for explaining.
So, you know, I mean, there's a little bit of work involved, but that's what happens sometimes.
Would it work to solve this by contradiction? So you would just take the second set, show that it's linearly independent, and then fail to show a case where the first set is dependent?
Well, I'm not sure that anything that you do is essentially different from what I just did.
Okay.
Let's see, 12. So problem 12 is you have a vector space V and some family of subspaces of V. And in general, if you have a family of subspaces, it's not the case that the union of all the subspaces is a subspace. But we have not just the union, but a certain condition. So we have the condition that for all I and j in the set I, there exists a k in I such that wi plus wj is contained in wk. We have this condition. Now, I want to prove this is a subspace. So the first thing you can say is, for any I, 0 is in wi for any I. So 0 is always in the union of these subspaces. In fact, 0 is in every one of them, but it only has to be in one for this to be true. And I want to show this is closed under vector addition. So let U and V, let me call this union W star, say. So that U and V be vectors in W star. So each of them is in one of the subspaces, but they don't have to be in the same subspace. On the other hand, so there exist I and J such that U is in Wi and V is in Wj. So U plus V, the sum of the two vectors, is in Wi plus Wj. And what we know is that this sum is contained in Wk for some k. So if I take any two elements in W star, the sum is contained in one of these subspaces WK, which is contained in W star. That is, U plus V is in W star. So this set is closed under vector addition. And that is closed under scalar multiplication is simple because if W is in Wi, then C times W is in Wi is contained in W star. So this is easily seen to be closed under scalar multiplication, but it's this condition which is sufficient to show that the union is closed under vector addition. That's the interesting part. Okay. Questions about this? Okay. What about number 13? So this is the fundamental theorem that leads to dimension of vector spaces being well defined. So we have S is a set of M vectors contained in a vector space V, and let W be the subspace generated by S. This means the smallest subspace of the vector space that contains these M vectors, which we know is the set of all linear combinations of these vectors. Let V1 be some sequence of N vectors distinct vectors in W. We want to prove that if N is greater than M, then the set of vectors V1 up to Vn is not independent, is linearly dependent. So how does the proof go? Well, all we know about these vectors is that they're in W, which means they're linear combinations of the W's. So for example, V1 is some linear combination, A11W1 plus A21W2 plus AM1WM, and so forth. Vn is A1NW1 plus A2NW2 up to AMNWM. And if I write down a linear combination x1v1 plus x2v2 up to xnvn, it's this times x1 and so forth. You have A11 x1w1 up to AM1 x1wm up to this last equation, which is A1n I'm multiplying this last equation by xn plus A2n xn. This is W1 up to AMN xn WM. And if I collect the scalar multiples of each of the W vectors, this is A11 x1 up to A1n xn W1, plus the second one would be A21 x1 up to A2n xn W2, and so forth up to this last equation. Well, up to the last, what do I get? Multiplying Wm, I have AM1 x1 up to AMN xn Wm is 0. So what can I say? I want to know whether there's scalars x1, x2 up to xn not all 0, which give me the 0 vector. Well, it's enough to show that each of the coefficients of the wi's 1 through m is 0. That is, can I find x's that solve the system of homogeneous linear equations a11 x1 up to a1n xn equals 0? Down to am1 x1 up to amn xn equals 0. What I have here is m homogeneous linear equations in n variables with more variables than equations. So there exists a non-zero solution. That is, I can find scalars x1 up to xn which solve all these equations simultaneously. And for those scalars, this linear combination of v1 up to vn is the 0 vector. So these vectors are not linearly independent. That's the proof. Let's see, someone asked about makeup for the exam. There really is no makeup because the exam is tomorrow night and I have to turn the grades in on Friday. So if for some reason you can't take the exam, the only thing I can do for you is to give you an incomplete. And then you have to go through the rather unpleasant process of getting an incomplete changed back to the grade you're supposed to get. Okay. Let's see. I'll do one more. Someone pick their favorite problem.
18.
18. Okay. So we have a linear operator on R2, which is as simple as it gets. T of xy is the vector 5x minus y, 3x plus 2y. And you have to remember, suppose you have a basis B for the vector space consisting of vectors, say, v1 and v2. Then you take T of v1, and this is going to be, this is in R2, so it's a linear combination of vectors in the basis. This is, let's say, a11 v1 plus a21 v2. And another way of saying that is T of v1, the coordinate vector with respect to the basis B, is a11 a21. And similarly, T of v2 will be some linear combination of v1 and v2. So let's call the coefficients a12 and a22. So T of v1, T of v2, the coordinate vector with respect to B, is a12, a22. And then the matrix for T with respect to this basis B is A11, A21, A12, A21. That's the definition of the matrix of linear transformation with respect to a basis. So if you take the simplest basis for E2, which is the unit vectors in the x and y direction, t of 1, 0, when x is 1 and y is 0, you get 5. When x is 1 and y is 0 for the second coordinate, you get 3. And t of 0, 1, when x is 0 and y is 1, you get -1, 2. But this is exactly, so this is t of E1, this is E1, this is E2, is 5E1 plus 3E2. T of E2 is -E1 plus 2E2. And so the basic matrix for T with respect to this basis E is 5, 3, -1, 2. That's kind of the simplest case. B is a little harder, and C is even harder than that. So let me look at C. Suppose I take B to be the matrix, to the basis 1, 1, and -1, 1, those two vectors. So I have to compute, so this is my V1 and this is V2. So I want to compute T of V1 and write it as a linear combination of V1 and V2. So T of V1, that's T of 1, 1. When x and y are both 1, 5 minus 1 is 4, 3 plus 2 is 5. And I want to write this as some linear combination of V1 and V2. That is A11 times 1, 1 plus A21 times -1, 1. This is A11 minus A21 and A11 plus A21. So I have to solve the equations, this equal 4 and this equal 5. If I add, I get 2A11 is 9. So A11 is 9/5. If I subtract the first equation from the second, I get 2A21 is 1. So A21 is a half. So in my matrix, so T of V1, the coordinate vector for that with respect to this basis B is 9/5, a half. And in the matrix for T with respect to B, this is going to be the first column, 9/5 and a half. And you calculate the second column by figuring out what is the coordinate vector of V2, T of V2 with respect to B. And whatever numbers those are what goes here. So you have to do some, I mean, what we're doing is reducing linear algebra to solving two equations and two unknowns, basic high school algebra. And it's always good when you can reduce something a little bit complicated to something easier. So that is the entire story. Okay, well, that's it for right now. And I'll be back online tomorrow at 10 o'clock if you have more questions.